Welcome back, everyone. Today we're doing a deep dive into PhysHS. That's the system letting humanoid robots like the Unitree G1 do some pretty complex stuff in the real world. Think of carrying boxes, sitting down on chairs, navigating the messy reality outside the lab. And our mission today, to unpack what seems like its secret weapon for actually working robustly out there, this innovative coarse-to-fine object localization module.
Yeah, and it's really crucial because continuous perception,
Yeah.
is just so hard for these robots. I mean, you could have amazing motion planning, but if the robot doesn't know precisely where that chair is,
Yeah.
well, it's not going to sit down right.
Right.
And standard onboard sensors, they struggle. Two big reasons. Cameras have limited fields of view, and things get blocked a lot, especially when the robot's moving around using its arms for these longer tasks.
Okay, so let's get into this dual stage solution that came up with. What happens when the robot's far away? Like the object isn't even in the camera view yet.
Right, so that's the core stage. It leans on LiDAR-based odometry.
Yeah.
Specifically, the G1 uses its fast LiO system with the Livox LiDAR. This basically estimates the robot's pose, its position, and orientation relative to where it started.
Okay.
It gives you this continuous, but coarse idea of where the object is. Good enough for long-range guidance, heading in the right general direction.
Makes sense. But how does it know where the object is to begin with? Is it just guessing?
No, not guessing.
Okay.
Usually at the very start, the initial course pose is manually set by an operator.
Mm-hmm.
They look at the LiDAR point cloud and maybe click on the object.
Okay.
And that gives the system its starting point before the robot starts moving.
Okay, got it. So manual input to kick things off, then the course guidance gets it into the neighborhood. But here's where it gets really interesting, right? That switch to precision. How does it refine things when it gets close for actually grabbing the box or sitting down accurately?
That's the fine stage. And it uses the head-mounted depth camera, an Intel RealSense D455 in this case, looking for an April tag.
Ugh, April tags, those little black and white squares.
Exactly. They're fiducial markers. Once the camera sees that tag on the object, it can calculate the object's pose really, really accurately. And that switch from coarse LiDAR guidance to fine camera April tag guidance, it happens automatically the moment the tag is detected.
And the improvement in accuracy is pretty dramatic, I hear.
Oh, huge. The data shows when it's just on course guidance, the average error is around maybe 0.35 meters. So over a foot off. Not great for precise tasks.
Definitely not for sitting down.
Right. But once it gets within about 2.4 meters, the camera spots the April tag, the fine stage kicks in, and boom, the average error drops way down to just 0.05 meters.
Wow. Okay, so 2 inches. That's a massive difference.
It really is. And the system's designed to be robust, too. What if it temporarily loses sight of the tag?
Mm-hmm.
The robot turns its head or its arm gets in the way while it's getting ready to sit.
Yeah. What happens then? Does it just stop?
Nope. It holds on to the last known accurate pose from the April tag and keeps updating it using the ongoing LiDAR odometry. So it maintains this continuous perception, this understanding of the scene, even with temporary blind spots, which is absolutely critical for finishing those long, complex tasks.
So pulling this all together, what does this clever perception system mean for, the big picture of getting these robots out into the world?
It's a key enabler. Honestly, this robust coarse-to-fine perception is a huge reason why PhysHSI achieves such high success rates in zero-shot sim-to-real transfer. They even made the simulation training harder, mimicking these real-world issues, like masking sensor data when the object would be out of view. So the policy learned to handle imperfect sensing right from the start.
So the takeaway here seems to be that bridging that sim-to-real gap isn't just about clever movement or control. It's about smartly fusing different sensors. LiDAR for the big picture, cameras for the fine details to build this continuous, trustworthy perception.
Precisely. Combining that long-range coarse guidance with the close-range fine precision makes the whole system work well, makes it portable, deployable even outdoors, without losing that critical accuracy.
Okay, so here's a final thought for you to chew on. Right now, they need that physical April tag to hit that super low 0.05 meter error. How far off are we, do you think, from AI achieving that same level of precision, just using cameras and visual understanding, visual SLAM, object recognition, without needing any physical tags at all? That feels like the next big step for truly independent robots, doesn't it?